Logistic regression looks simple. Take an input, multiply it by weights, add a bias, pass it through the sigmoid function, and get a prediction. But here's what's interesting. This is already a neural network. And by adding more neurons and layers, we can build something much more powerful. Let's start with a simple problem. Suppose we want to find cats in images. A 64 by 64 color image contains 64 by 64 by 3 values. We flatten those values into a vector, pass them through logistic regression, and get a number between 0 and 1. Close to 1 means there's a cat. Close to 0 means there isn't. But what if we want to recognize a cat, a lion, or an iguana? We add more neurons. Each neuron receives the same input and produces its own prediction. And if only one animal can appear in the image, we can use Softmax. Softmax turns the outputs into a probability distribution, where the probabilities add up to 1. Now the network can decide which class is most likely. But the real power comes when we add another layer. This creates a hidden layer. Now the network can start learning representations of the data. In an image, the first layer sees pixels and can learn simple patterns such as edges. The next layer can use those patterns to build more complex features. And as we go deeper, the network can understand increasingly complex information. The important part is that we don't manually tell the network what features to look for. We give it the inputs and the correct outputs. The network learns what matters. This is called end-to-end learning. The same idea works for something like house price prediction. Instead of manually deciding which features matter together, we fully connect the network and let it figure out which information is useful. That's also why neural networks can be called black box models. We don't always know exactly what every neuron has learned. But with enough data, the network can discover complex patterns. Now we have the network. But we still need to train it. We initialize the weights and biases. Then the input moves through the network. That's forward propagation. The network produces a prediction, and we compare it with the correct answer using a loss function. Then gradient descent updates the weights and biases to reduce the loss. When we calculate the derivatives by moving backward through the network, that's backward propagation. And when we have many examples, we can process them as a batch and parallelize the computation. This matters because deep learning can be extremely computationally expensive. Its progress was helped by more available data and more computational power, especially GPUs that allow these calculations to be parallelized. So the basic story is simple. Logistic regression gives us the building block. A neuron combines a linear operation with an activation. Multiple neurons form layers. Hidden layers learn increasingly complex representations. Forward propagation produces predictions. And training uses the loss and gradients to improve the parameters. But one question remains. How do we decide how many neurons and layers a network should have? There isn't one perfect answer. Different architectures have to be tested and compared using a validation set. And that's where designing neural networks becomes an engineering problem of its own. In the next video, we'll dive into backpropagation and how we improve neural networks.